All right, let's get started. We have 1 minute till Jacques can start his talk. So I'll first introduce our first invited speaker of today, Jacques Kluska from KU Leuven, and he will talk to us about circumbinary disks in post-AGB stars, disk binary interactions, and second generation planet formation. So Jacques, go ahead and share your screen, and yeah, please start your talk.
All right, I hope you can see my screen and you can hear me
See
well.
and hear you, perfect.
Okay, great, thanks. Okay, thank you very much for giving me the opportunity to talk about those very exciting targets that are the post-AGB binaries and their circumbinary disks. So I want first to acknowledge all my collaborators with whom we are working to understand further those targets. All right, so the post-AGB phase is a transition phase between the asymptotic giant branch phase that was described in few toasts earlier this morning, and the planetary nebula and the white dwarf phases. And so this transition is characterized by a very high luminosity that stays more or less constant, and an increasing temperature due to the contraction of the white dwarf. And actually this is a nature diagram for a singular star, but I will talk about post-AGB binaries. And so at the end of the giant branches, if you have a companion, the giant star will interact with this companion through Roche-lobe overflow or even a common envelope evolution phase. And so this interaction will end up by where the atmosphere of the giant star will be expelled, and parts of this mass will remain bound to the system and form a circumbinary disk. So how do we see those disks? So we do not understand how the disks are formed, but we observe those disks. And so how do we detect them? So first we can detect them through the infrared excess in the spectral energy distribution of those targets. So here we see the flux against the wavelengths, and we see two kinds of infrared excesses. So we see a shell-like excess where we see a black body emission at a single temperature, and a disk-like excess that is more smooth, and that corresponds to all the different temperatures that are in the disk. And actually, we can monitor those targets with radial velocity measurements and to look for companions. And we see that the targets that have a shell-like excess are single, and the targets that have a disk-like excess are binaries. So there is a very strong link between binarity and the presence of a disk. And now, as we have the binary orbits, we can see if they agree with theoretical predictions. And so what we expect from binary interaction is that you have a bimodal period distribution, where you have short periods due to a common envelope evolution where the companions spiral in, and long periods due to wind interaction where that Y will widen the orbits. And actually the observed orbits lie really between those two modes. So there are some ingredients from binary evolution that we do not understand. So this is why it is interesting to study those binaries and those disks, because they are products of the binary interaction. Maybe they can resolve this orbital tension that I just mentioned, because there are some disk binary interactions. So we saw from hydrodynamical simulations that resonances between the disk of the inner binary or accretion of mass from the disk to the binary can change the binary orbits. And I will show you that I will try to convince you at least that this disks are very similar to what to the disks that are seen around young stars. And so maybe this raises the very exciting question of second generation planet formation in those disks. And so here in this talk, I'll focus on specially resolved observations of the inner disk. So first, this is an artistic impression of such a system, where you see the inner binary, so the post-AGB star, the companion that is a main sequence star. It has it has some jets from the from the companion, and there is a disk. And so the disk is stable, as we see from CO observations, large-scale CO observation from ALMA and Plateau de Bure interferometer, where we probe the Keplerian rotation, basically, of the gas. We see that the dust grains are quite large, so there is dust grain evolution, and that we see jets and outflows. And actually, if you want to know more about jets, just stay on this on the Zoom to listen to the talk of Dylan in 20 minutes. And so all these properties are also seen in young stars. And so to give you an idea about the scales that we see in those targets, so the binary separation is around 1 astronomical unit. The disk inner rim in the dust is 15 astronomical units, and the outer rim is around 100 or more astronomical units. And so the typical distance of those targets, which is 1 kiloparsec, 1 astronomical unit is 1,000 of an arc second. It's 1 milliarc seconds. And so we really need to use high angular resolution to try to spatially resolve those targets and to have to study their structure. And so what we'll use is the VLTI, so the Very Large Telescope Interferometer that is in Chile, that can combine few telescopes, and that gives us access to this 1 astronomical unit angular resolution. So in the near infrared, we'll mainly probe the emission from the inner rim, so very the start of the infrared axis, and the mid infrared will probe the inner disk structure. And at longer wavelengths, you can probe the larger structure. Okay, so in this talk, I will focus on 4 parts. So the first part, I'll describe the building blocks that are observed, mainly around one system. Then I will switch to the snapshot surveys to see if those sketches also seen those building blocks are also seen around all the targets. Then I will speak a bit about the need for imaging, so interferometric imaging, and I will finish on the disk evolution that we see. Okay, so the building blocks. So I focus on RS-08, which is a binary with an orbital period of 500 days and an eccentricity of 0.2. Here we see the radial velocity measurements, and that has a very nice disk-like LCD. And we obtained VLTI pioneer observations in the near infrared of this target. So we see here the squared visibilities and the closure phases that are the interferometric observables. And so the visibility is probed the size, basically, of the emission, and the closure phase, this asymmetry. So if you have non-zero closure phase, we see that there is a degree of asymmetry in this target. First, we wanted to reproduce both the ACD and only the squared visibilities with a simple axisymmetric radiative transfer model in order to have the radial structure of the disk. And we managed to do so with a radiative transfer model that was used for protoplanetary disks, actually. And so the main information that we get from this model is that the inner radius is at the theoretical dust sublimation radius at 8 astronomical units from the central binary, and that we systematically need a double power law to reproduce both the interferometric data and the LCD. And this was also seen in the few other targets that were modeled so far. And there is a dust mass that is quite high, although it's not very well constrained by this data, but it's also similar to what we see around young stars. Actually, now with all the 3 instruments that are available at the VLTI, we can really probe the inner disk structure from the near infrared, so from the inner rim, to a few tens of astronomical units. And so this is the work from Ake Corporal, that is a PhD student here. So I don't have time to dig into that, but stay tuned. The paper will be submitted very soon. Okay, so we have this model, axisymmetric model, that is reproducing the data, but we wanted to know what the data is really telling us, because we see that there is some closure phase signals, some non-axisymmetry. And so we went for image reconstruction. And actually, it shows up it shows very nice the building blocks of the system. So the first image reconstruction we did is this one. So it's a monochromatic image reconstruction, and it is dominated by the central star. So, okay, we see the star, it's around half of the emission. And we can remove the star in the Fourier, in the Fourier domain using the Sparko approach. And what we see is what is around the star, so its environment. And so we see unexpectedly an emission from the position of the secondary. And this was unexpected because the secondary is a main sequence star. So the contrast is so high that we should not be able to detect it. But what we think we see is the accretion disk around the secondary that is also linked with the jets that we see from the secondaries. And we see the ring, that is the dust sublimation front of the disk, basically. And so if we also subtract the secondary from the image, we see that this dust, the disk inner rim is very compressed, perturbed. So we see, for example, two maximas. One is probably due to the illumination from the primary that is closer to this part of the disk, but the second could be a density wave, a spiral wave that we are probing. And what we do not see in this image that there is an over-resolved flux. So there's emission coming from larger scales, around 15%, that cannot be reproduced by the radiative transfer model, and that the origin is unknown, but we think it's scattered light, so stellar scattered light on the disk surface or on the outflow. So what we want to know now is that is this system common? Are those building blocks common and seen around other systems? So what we did is we did a snapshot surveys, interactive snapshot surveys. Why a snapshot is because we cannot making an image takes a lot of time, and so we just want to have a few interferential observables to see if we are in the right ballpark. And so we observed 23 targets with Pioneer, so same instrument that RS-08, and we fit them with geometrical models with increasing complexity. So the models were inspired by the image, so the building blocks that I just showed you, but we started with very simple models with 2 or 3 parameters and ended with around 17 parameters. And so the main conclusions that we have is that the near-infrared emission morphology is complex. So most of the targets prefer complex models with more than 10 parameters. And so we really need to do the imaging to not be model biased and to understand what we are looking at. The second conclusion is that the observed inner rim is set by dust sublimation as opposed to, for example, dynamical truncation. So here we have the size that we observe, and this is the binary separation, and this is the size that we expect from dynamical truncation. And the observed size is always larger than that. And we also see that the size compared to the luminosity of the star follows the square root of the luminosity relation as expected with the dust sublimation inner rim. And as it is also seen around young stellar objects, although there is a shift in the sizes that can tell us something about the density and the mineralogy in these disks. And finally, we also probed the radial structure with the sizes of the emission in the near-infrared here and the mid-infrared. And so what we expect is that there is a relation between the two sizes, and if you have a continuous disk, we will be in this yellow area. And so most of our targets are compatible with a continuous disk, even though there are some outliers. Okay, so this emission is complex. And so we need to do image reconstruction at the end in order to really recover understand those targets and understand the emission in the infrared. So we obtain actually another image of one such a target, which is HD11584, which is famous for its ALMA image, where we see this bipolar morphology with jets, with outflows, and also the disk. And actually, if you zoom in, this is the image that you obtain. So with 3 millisecond scale imaging, here we subtracted the central star. And what we see the ring, and actually we see 2 rings around this target. And we can measure the temperatures. And so the inner rim is about 1500 Kelvin and the outer rim is a bit colder, around 1000 Kelvin. And so what we think is that because there's a slight shift between those two rings, we think that the outer ring is actually coming from, is not in the disk plane, but is likely probing the outflow and possibly linked with the outflow structure that you see in the large scale. So it could be either the dust condensation front in the outflow or another density linked with the episodic outflow event. So we need images, and so we need to probe more targets in order to have start to have a larger sample and have more definite conclusions of the morphology of those targets. And this is why we started a large program, which is called Inspiring at the VLTI, in order to image 11 targets. And to image 11 targets, we need 250 hours of observations on the VLTI. And so the goal is to probe the structure of the inner rim and to link it with the binary phase, see if we detect the secondary accretion disk, and look for an evolutionary sequence. And so the methodology is that we develop some image reconstruction tools using actually neural networks that was developed with my master student, Rick Kless. And then we use geometrical modeling to have an insight in the morphology, and we finish with radiative transfer modeling to really recover the density structure of the target. And so we see that we have very large diversity of morphologies. So those are very preliminary images. And for one of the targets, we have 3 epochs, imaging epochs, and we see that we detect the secondary at different orbital phase, and we see that the morphology of the inner rim is changing. So that's very exciting, and we are now trying to figure out to explain what we see basically. Okay, and I will finish with disk evolution. And so actually it's not high angular resolution observations, but it's just using the information, the near and mid infrared, to try to spot the disk evolution. And so I focus on IRAS-08 at the beginning of the talk, and we see it's a nice full disk, but actually there are also disk SEDs that are a bit different, where the infrared excess starts not in the near infrared, but in the mid infrared. And what we think is that this is due to a disk with an inner hole. So, and actually this kind of disks are seen also around young stars, where we see that there is no infrared excess in the near infrared, but then the infrared excess starts later on, and those are called transition disks. So I'll also call this disk transition disk as to make the analogy. And so if you look at the near infrared excess, it's very different between those two targets. And also the mid infrared, you see that the color will be very different for those targets. And so we can use those near infrared colors and mid infrared colors to put them on a plot and try to classify those targets. And we see that there is structure in this color diagram. So we see that there's a lot of targets that have no or very low near infrared excess, but a large mid infrared excess, and targets that have near infrared and mid infrared excess. And so we try to reproduce this color diagram with radiative transfer models. And so here you see in orange the full disk models, where we vary parameters such as inner radius or inner density parallel, and transition disk models. And we see that we can reproduce with those two models the population, the observed population. And actually, this color diagram is quite powerful because the different areas in this color diagram represent different kinds of infrared excesses that are probed. And we think that we really probe disk evolution. So we have here very high infrared excesses. Then you have the more classical full disk like IRAS-08 in red. We have transition disks in blue here, like AC-HER, that is here. And then in yellow and the green, we have less massive disks until we reach excesses that are very weak, and that stars are very long wavelengths, like debris disks. And so we are now trying to figure out what is happening, and if we can explain those different SEDs with disk evolution and compare that to what we see, what what the disk evolution that we see around young stars. So we start with a full disk, we go to a transition disk. When we have disk dissipations, we have lower mass, so lower excess, and then we end up with a debris disk and maybe also some planets. Okay, so, and this is my conclusion slide. So the infrared interferometry is a very nice tool in order to image this binary interaction and probe the inner disk structure. The inner disk is, so the dust inner rim is ruled by dust sublimation, but doesn't mean that there is no gas inside this inner rim, and that it is perturbed by the inner binary. We detect accretion disks in around half of our targets in the large program, but this will be a result that will come. And there is a large diversity, and so we think that we probe disk evolution. And there are many similarities with protoplanetary disk in terms of structure, as we can reproduce it with models of protoplanetary disk actually, in evolution, and also dust evolution, for example. So maybe if we can probe the dust structure even more and use multi-wavelengths and multi-scale observation, combining so interferometry, infrared interferometry with ALMA and sphere, we can say more about this exciting possibility of planet formation. And so we want to probe this structure, so see if there are gaps, if the disk is warped, for example, by the presence of a first generation planet, and if we see spirals, things like that. And then we need to, of course, come back to the models and reproduce all the observations with radiative transfer modeling. And we need more and more complex models to reproduce such a structure, so 3D radiative transfer models and also hydrodynamical simulation to probe the disk binary interaction. And so I think we are really heading towards a global and very exciting time where we have a global understanding of this disk for binary evolution and also perhaps second generation planet formation. Thank you very much.
Thanks, Jacques. Thanks for the very interesting talk. We already have a question from Patricia. Please go ahead and ask your question.
Thanks very much. That was very interesting. Can you say what fraction of the sources you're reasonably certain are single stars, or could they all be binary systems?
So the fraction of the disk sources that are binaries, so it's around 98%. So the binarity and the disk, so the presence of a disk is really linked to binarity. So there are few targets where we do not detect a secondary, but it could be that it's a longer period, for example, but almost all of the sources are binaries.
So we really don't know anything at all about post-AGB stars, single stars, even though all the theoreticians model single star in the post going into
No, we know. So I really focused on the binaries.
Okay.
Yeah. No, there are post-AGB single stars. Okay. I thought that the question is about how many disk sources are binaries.
Fair enough.
But around single stars, we do not see disks. Yeah.
All right, thanks. We have time for another quick question. So please raise your hand in the chat. Aha, I see a hand. Yes, Lee, please go ahead.
Hi, Jacques. Thanks for the really excellent talk. I was wondering if there's any way to sort of distinguish between the disk scenarios in the optical. I mean, sort of the H alpha line immediately sort of springs to mind. I sort of wonder what you'd expect from these different scenarios in that profile.
Yeah, so the H alpha is actually probing the very inner regions, and so we think it's probing emission very close to the star, so not the circumbinary disk. So it's probing the jet from the secondary, and also accretion disk. We think that it's probing also accretion disk around the secondary or the primary. So there is H alpha emission, but it's not probing the circumbinary disk. For other all the lines, I think the optical, they are mostly probing really, really close to both stars and not the circumbinary disk itself. So we really need to go for longer wavelengths to probe the circumbinary disk.
Right, thanks for your questions. If anybody has other questions to Jacques, please ask them on Slack. And then now I ask, it's time for Dylan. Please go ahead and share your slides. So Dylan Bollen is also at KU Leuven, and he will talk to us about the tomography of jets in post-AGB binary systems. Okay, Dylan, I'm going to give you a 2-minute warning. Go ahead.
Yes, you can hear me and see my screen?
I can hear you, see your screen, and see your cursor.
All right, great. So thank you, Marie, for introducing me, and thank you to the LOC and SOC for giving me the opportunity to talk about my work. So today I will talk about jets that are launched from post-asymptotic giant branch binary systems. Now, Jacques already gave a nice introduction about post-AGB systems. Here I will mainly start with an overview of these systems and all of the components that are involved. So we have a post-AGB star, which is part of a binary system. So we also have a companion star, which is most likely a main sequence star. And so this binary system is surrounded by the circumbinary disk that Jacques talked about, which was created during the preceding phases. And so there is also evidence that matter from the circumbinary disk is being reaccreted again onto the two binary components. And we know that this post-AGB star still has a stellar wind. And as you can see here, there's also a smaller accretion disk around the companion star. Now, this smaller accretion disk can be created or can be fed by one of two components. It can be either created by a mass transfer from the post-AGB star to the companion, or from these reaccretion streams. And then it's from this smaller accretion disk that a high velocity outflow or jet is launched. And so here I will just refer to these as jets. So now, how do we detect these jets? Well, during the past 13 years, we've collected hundreds of high resolution optical spectra for about 60 of these post-AGB binaries with the Hermes spectrograph, which is mounted on the Mercator telescope in La Palma in Spain. And so when we look at the Palmer lines of these systems, so the Palmer lines in these spectra, and mainly the H-alpha line, we notice a very interesting variation that occurs over time. So these H-alpha lines change from a double peaked emission with a central absorption to a more P-Cygni-like profile. And we can plot this in these dynamic spectra as well. So here on the x-axis, we have radial velocity or wavelength, and on the y-axis, we have the orbital phase, so the phase in the orbit. And the color is an indication for the amount of flux that is received. So a slice at orbital phase 0 would correspond with the phase when the post-AGB star is closest to the observer and the companion star is in the back. And this is when we see this double peaked feature. At orbital phase 0.5, that's when the two stars have swapped position. So the post-AGB star is in the back. And this is when we observe this absorption. So this absorption can be explained by the presence of a jet. So again, if you're looking at the system at orbital phase 1, we are looking at the system from here, where my pointer is, and we're directly observing the post-AGB star with the companion star in the back and the jet. Then half an orbital phase later, our line of sight will start to go through the jet towards the post-AGB star. So this means that the photons from the post-AGB star will be absorbed by the hydrogen atoms in the jet, which travel at high velocities. And that creates this blue shifted absorption feature. So this also means that due to the orbital motion of that binary, we are always probing different regions in that jet. So this gives some kind of tomography of the jet. So now, as I said, we have observations for about 60 post-AGB stars, and we find this jet feature in about 50% of them. So that shows that the jets are really common in these post-AGB binary systems. And also, I've plotted 17 dynamic spectra for 17 objects. You can really see that all of these absorption features are really diverse for all of these objects. So now we have all of these observations. What can we do with them, or what can we learn from these observations, and what have we done? So we started with making a spatial kinematic model of the jet in order to determine its full structure. Then we made a radiative transfer model in order to determine how much mass is lost by those jets. And then we used those results in order to investigate what the source is that feeds that smaller accretion disk around the companion. So first, let's go into the spatial kinematic model, with which we determine the structure of the jets. So we have a jet binary model, the post-HB star, and the jet with its accretion disk. And the jet has a certain velocity structure, an opening angle, and a density structure. And if we then zoom in this model into those innermost regions, then you can see that we assume 3 possible jet launching mechanisms. So the first one being a stellar jet, where the material is launched along the open magnetic field lines of the companion. The second one is a disk wind, where the material is launched above and below the midplane of the smaller accretion disk. And the third one is an X-wind, which is similar in nature to the disk wind, but where the material is launched from those innermost disk regions. So now we have this model of the jets, but how then do we get the actual structure of the jets? Well, we start by giving an initial background spectrum to the model with no jet absorption. Then we select a certain number of jet parameters, and so we create a jet model. And then for that model, we determine how much absorption will occur in the spectra. So we get this synthetic absorption feature, which we then fit to the observations. And we then use an MCMC fitting routine in order to find the best fitting jet parameters. So we've done this for those 17 objects that I showed you before. And as you can see, the model does an amazing job in recreating those spectra. So every time on the left, we have the observations, and on the right, the model. And for 89 Her, for example, the absorption feature is always present throughout the orbital phase. And that's nicely reproduced by the model. But also, these shorter absorption features are recreated by the model. And even these more unusual shapes, like for HP Lyrae and TWCAM, the model can reproduce these. So this really shows that our spatial kinematic model can reproduce this whole diversity of absorption lines. But also that shows that we can really isolate the most important jet and binary components. If you look at 89 Her again, for example, that absorption feature is always present. And if you look on the left, we have a representation of the best fitting model. So here we have the post-HB star with the line of sight, the companion star, and the blue is the jet. So you can see that the model predicts a system where we have very small inclination angle. So even when these 2 stars have swapped position, we will still be looking through the jet. So that absorption is always present. This is not the case for this object, PD. If this inclination angle is much larger, so if the post-HB star and companion star have swapped positions throughout the orbit, we will no longer be looking through the jet, so that absorption is only present for a short period of time. But also other components like jet velocities and jet angles can be determined from all of this. So if you look at our results, then we find that in general, these jets are pretty wide. So they have opening angles larger than 30 degrees and outflow velocities, which range between 150 and 800 kilometers per second. And that's a strong indication that that companion star is a main sequence star, since the jet velocities are always on the order of the escape velocity of the jet launching object. And then we also find a significant jet tilt. So here we are looking at these systems edge on again, but now the post-HB star is directly behind the jet and the companion. And as you can see, these jets are tilted with respect to the orbital axis of the binary system. And so that can be explained by one of 2 things. It could be either a a precessing jet that causes this, or maybe it could be jet deflection, so where the jet is deflected due to the orbital motion of the binary. And then, as I mentioned before, we have 3 jet launching mechanisms. And quite often the stellar jets or the X-Wind configuration will give the best fitting solutions, but we can't always differentiate between 2 or sometimes even 3 of these jet launching mechanisms. And this is because we probe the jet relatively high, so far away from the jet launching region, which makes it more difficult to determine the actual jet launching mechanism in these systems. And so then we go into the radiative transfer model for the jet. So in this radiative transfer model, we used the output from the spatial kinematic model, so the jet structure, as input. And now we will determine the absolute density structure of the jet, which we did not do before. Before we only got a scaled density structure of the jet. So this again works pretty similar as before. We follow the light from the post-HB star, and when that light shines through the jet, we will divide those rays up in a certain number of grid points, and then start at the first grid points, calculate the local density, velocity, and temperature, determine to which wavelength bin that corresponds, calculate the absorption, and then we iterate over all of those grid points to get the whole absorption feature. And so now we model the first 4 Balmer lines, H alpha, H beta, H gamma, and H delta. And what we fit is the equivalent width of these lines over the orbital phase, since this can be used as a proxy for the amount of absorption by the jet. So as you can see, the jet absorption is strongest in H alpha, and then becomes weaker in H beta, H gamma, and H delta. And that's also shown here with these equivalent widths, where you have equivalent widths as a function of orbital phase. So for H alpha, for example, the equivalent width will peak at an orbital phase close to 0.5, which corresponds to this phase. So by fitting these, we can determine how much, we can determine the densities and temperatures in the jets. So now we have the jet density structure, we have the jet velocity structure. We can determine how much mass is actually lost by these jets. And what we find is that the mass loss rates in these jets are pretty high. They're about 10 to the minus 7 solar masses per year, but they also have a quite high, quite a large range. So in some cases, we find a jet mass loss rate of 10 to the minus 4 solar masses per year. Now, since we know how much mass flows out, we can also estimate how much mass is accreted in this smaller accretion disk. So if we assume that about 10 to 30% of the mass that is accreted will eventually be ejected, then we can we get an average mass accretion rate of about 10 to the minus 6 solar masses per year. And now we can use these results in order to determine what the source is that actually feeds that smaller accretion disk. So we have 2 plausible sources. The first one being the post-HB star, which can transfer mass via stellar wind, and the second one being this re-accretion from the circumbinary disk. So in order to compare those, we plot the jet mass loss rates for each object, which is shown here on the x-axis. So that's what we found from the model. And we estimate a possible mass transfer rate from either the post-HB star to the companion or the circumbinary disk to the companion. And these are here on the y-axis. This line of 1 represents the case where all of the accreted mass will be ejected by the jets. A value of 0.1 indicates that 10% of the accreted mass will be ejected. And everything that falls below this line would indicate that more mass is ejected than the amount of mass that is accreted. So that's not physically possible and could mean that either we overestimated the jet mass loss rates, or that particular mechanism cannot explain those observed jet mass loss rates. So if we then compare those 2 possible sources, then we find that the circumbinary disk gives a better explanation for these jet mass loss rates. So we conclude that the circumbinary disk is most likely the dominant source that feeds the accretion disk around the companion. This does not mean that the post-HB star does not transfer any mass to the companion at all, but it rather indicates that the mass transfer rate cannot sustain the observed jets. But it's important to note that we don't have a full picture yet, because for two objects, we get very large massless rates, and we cannot explain this by accretion from either source. So yeah, future work is still needed on this. So yeah, to conclude, we have this spatial kinematic model, which contains all physical parameters that explains the whole jet diversity, and we can isolate the most important jet components. From our radiative transfer model, we determined that the massless rates are pretty high, and so are the mass accretion rates. And we find that the circumbinary disk is most likely the dominant source that feeds the accretion. So this is what has been done, but there's still a lot of work to be done. So in particular for our models, we want to better constrain the jet launching mechanism and improve upon our jet model by including some other components. Then we would also like to use 3D radiative transfer codes that already exist, where we can use our results as inputs and then maybe include some other components like an accretion disk around the post-HB star. And we would also like to explore the systems in different wavelength regimes, since I only looked at the optical. Thank you.
Thank you, Dylan, for a very interesting talk. It was in fact so interesting that I forgot to give you the 2-minute mark, but you kept well within the time, so that worked out great. So if anybody has a question for Dylan, please raise your hands and then you can ask your question either in the chat or verbally. Aha, there is a raised hand. Leen, go ahead and ask your question.
Okay, thanks, Mary. Thanks, Dylan, for your interesting talk. I have actually 2 questions. First of all, for if you're modeling the jets, how are you dealing then, for instance, with what kind of temperature structure have you assumed in your jets?
Yeah, good question. So initially we assumed a isothermal jet.
Yeah.
So that's something that we're working on now to include a temperature gradient in the jet itself.
Okay, yeah, I can see. And then the second question, since your jet has such a high velocity, 2 things. So do you then take the velocities along the way being constants, or do you allow for the projected velocities to change and as such implement that in the blue-in condition?
Yeah, so we allow for the projected velocities to change. So we assume a certain jet velocity structure in the jet. So mainly at the outer jet regions, the velocities are lower, and then in the central regions, the jet velocities are much higher. So that's relatively flexible in the model. So that's included that we don't assume a single jet velocity along that ray.
And then you implement that in the blue-in condition for your radiative transfer calculations?
Yes, indeed, yeah. So then we get that result from the spatial kinematic model, and then we give that as input into the radiative transfer model.
Yeah, okay, good, thanks.
Thanks, Leen. If anybody else has a question, please go ahead and ask. Yes, please, Maxime.
Good afternoon, everyone. Thank you for a very informative and very beautiful presentation, Dylan. I was wondering, it may be a stupid question, but I was wondering what is the source of your estimation from 10 to 30% of accreted matter going through the jet? Why exactly this amount of percentage?
Yeah, so I looked at several studies where they try to estimate that jet efficiency, which is a very tricky thing to estimate because it's all based on empirical results. But I mainly base that on YSOs. So I look at, just try to collect as much YSO studies that looked at this jet efficiency and then assumed a similar jet efficiency, because these jets are very similar to those jets that are found in young stellar objects.
I see. Thank you for the answer.
All right, Shazreen, a very quick question.
Very quick, sorry. Thanks, Dylan. I was wondering just along those lines, because you mentioned it, have you compared your jets in these systems to the ones that we find in symbiotic binaries, like our query, for example, or in some of the PN that we find, like M29, and how do they compare?
Yeah, so I haven't compared them that much to those jets yet. That's also part of something that we're planning on looking into more.
Great, thank you. Thanks, we can chat more on Slack. Thanks.
Yeah.
If anybody has another question, please ask Dylan on Slack. There's the day one channel specific for questions on this day. So thank you again, Dylan, for your talk. And then now, Yael, if you could go ahead and share your slides. So Yael Hillman is from Ariel University, and she will talk about classical novae as a result of wind accretion from an AGB star. I will do my best to give you a 2-minute mark, Yael. Please go ahead.
Okay, thank you. I've been modeling classical nova and recurrent nova for a while, and recently thought of checking what would happen if we would try to get a classical nova from the wind of an AGB star instead of just from a main sequence star. So I'll start with just very quick general description of what a classical nova is. So it's an eruption that occurs on the surface of a white dwarf in a binary star when the white dwarf is actually accreting mass somehow from its companion. And since this mass is of solar composition, it builds up when it reaches a critical amount of mass. It burns the hydrogen in a thermonuclear reaction, ejects all the mass that it has accreted or part of the mass that it has accreted, which looks like a very strong brightening. So that would be a nova eruption. So any binary star will have Roche geometry, and if they're far enough apart relative to their radius, relative to their structure, so they would be detached, and then there would be, if it's a main sequence star, the companion is a main sequence star, so there'll be no mass transfer. But for classical nova, what we have is they are close enough together for the donor, which, as I mentioned, main sequence, which I'm calling here a red dwarf. It's usually a low mass main sequence. So then the donor will be filling its Roche lobe overflow, its Roche lobe, and there will be Roche lobe overflow through the first Lagrangian point. So mass will be spilling through this point onto the white dwarf. There may be a disk, may not be a disk, but eventually it falls onto the white dwarf. And then we get the classical nova. I'll just mention that recurrent nova is basically the same as a classical nova, just that the same system has been observed more than once. But then we have symbiotic nova. Symbiotic nova occur in symbiotic systems with a more evolved companion, a red giant or a star in the AGB, and this is unlike a red dwarf or main sequence. These have very strong winds, and the white dwarf can be accreting mass from the wind, even if they are the binary component can even if the stars are far enough apart to not be in contact. So we can have no Roche lobe overflow and plenty of wind passing through the white dwarf's area, and the white dwarf can capture that mass. There can also be a state where the giant is filling its Roche lobe, and then the mass transfer will be much more complex because there will be Roche lobe overflow and wind. Both of these are seen. I will just explain just a slight difference between classical nova and a symbiotic nova. So I mentioned that a classical nova is from a thermonuclear runaway, and the typical brightening of a classical nova is a few tens of thousands of solar luminosities. And a symbiotic nova which is not a classical nova. Different mechanisms may cause it, and that's not what I'm focusing on here. But this is what we mostly may see in these sort of systems. And then the brightening is a lot lower. Another difference between the two is the accretion rate. Accretion rate for classical nova is, say, up to a few times 10 to the -8 solar masses per year. And the accretion rate for a symbiotic nova is much higher. I wrote it here very, I don't know, conservatively, but the difference may be even more than this. And this just tells us that the rate of accretion onto the white dwarf is what determines what's going to happen there. Will be determined if we'll see just a weak symbiotic nova or if we can see a classical nova. And normally in systems with, in symbiotic systems, which have a giant companion, we will see symbiotic nova, and the classical nova are reserved for the main sequence donor. But what if we can actually get the accretion rates required for classical nova in systems with a giant donor? So that's the question that I am asking. And then I go to see what kind of accretion rate I can actually get from these symbiotic systems. So obviously, the wind rate will have a very high influence on what the accretion rate will be. If we look at an S-type companion, the wind rate is very similar to what we actually need for classical nova, and a D-type companion is much higher. Their radiuses are much different as well. But just looking at the wind rate is not enough. We have to see how much of the wind will actually be captured, because the wind is blown in all directions and only part of it passes through the white dwarf's area. So for that, we have the Bondi-Hoyle-Littleton accretion. This scheme was made for a stellar object that is moving within a cloud. And then there is relative motion between them. So there is a density and velocity, and the stellar object will accrete some of the mass that it's moving through, some of the wind, some of the cloud that it's moving through. But this can just as easily be applied on a white dwarf that is sitting in the wind from a giant. It's same idea. There's relative velocity between the cloud of gas and the white dwarf. So it's easily applied to this. And the Bondi-Hoyle-Littleton prescription calculates the accretion rate based on the density of the wind, the velocity of the wind, and the gravitational pull of the stellar object, which in our case here would be the white dwarf, which of course the gravitational pull is directly dependent on the white dwarf mass. Now, from stellar evolution of an AGB star, we get the density of the wind and the velocity of the wind, and they are dependent on the rate of the wind loss rate, and the separation of the binary. So the bottom line of all this is that the accretion rate is depending on the white dwarf mass and the separation. The accretion rate would be between a 10th and 100th of the wind rate. So if the wind rate, where was that? Where did I have that written here? So if the wind rate from, say, an AGB is about 10 to -5, -6 solar masses per year, that could give us an accretion rate similar to what we may get from a classical nova, of course, depending on separation and such. So what do we actually see? What are observed? So symbiotic systems, of course, normally will just show symbiotic nova, but some of them do show classical nova eruptions. They are not very common, but there are some. And the question is, or the question that I was asking was if these classical nova that are seen in the symbiotic systems, if they result just from wind accretion, or if Roche lobe overflow is involved as well. And to determine that, we just have to look at the separation. Like if the donor radius is of same order as its Roche lobe radius, then there may be Roche lobe overflow as well. But if they're far enough apart for the Roche lobe radius to be much larger than the donor radius, then we can assume that it is only wind accretion. So I was looking for some systems like that in the literature. Why isn't it moving there? And the first ones I found were actually, and these aren't AGBs, these are younger stars, red giants. But there's RS Ophiuchi, which is a recurrent nova. Every 20 years it erupts. And it is erupting as a classical nova. So we do see nova, and I'm interchanging recurrent nova and classical nova because they are basically the same thing, just it becomes recurrent if we see more than one. So I apologize if I replace those with each other. The orbital period of RS Ophiuchi is only 1 year, and the donor radius is more or less the same size as the Roche lobe radius. So there's definitely Roche lobe overflow involved in this system. V745 SCO erupted 3 times. And also here, the Roche lobe radius is about twice the size of the donor radius. So there may be Roche lobe overflow here as well. There's AGPEG, which erupted twice, which again, also here, there may be Roche lobe overflow, but there is also something very interesting in this system. And that is that the 2 eruptions behaved very differently. They had different amplitude of eruption, like they reached different luminosities. The time to decline was different between them, and the estimated accretion rate of each of them were also different. This is in correlation with a changing wind rate. So there could be Roche lobe overflow as well, but if the accretion rate is changing, so that implies that the wind rate was changing. So that's very interesting, at least I thought so. And then there are a few with AGB donors, and that are far enough apart to assume that there is no Roche lobe overflow. So there's V1016, which erupted in 1965. There is a wide range of estimations of what the separation may be, what the orbital period may be, but this system most probably has no Roche lobe overflow, and it had classical nova eruption. HMSGE, same thing, they are very far apart, had an eruption in 1975, classical nova eruption, and there, okay. Oh, really? Okay. And V407 Cygni, which in 2010 had a classical nova eruption. And what's interesting here is also that it had previous eruptions, but they weren't classified as a classical nova because they look very different, which again is in correlation with a changing wind rate. So inspired by V407 Cygni, which has a very wide separation, I performed a model of a wind model with a white dwarf mass of 1.25 solar masses and an AGB donor of 1 solar mass, and just let it run simultaneously and and have classical nova eruptions. And for comparison, I took a Roche lobe overflow model with a main sequence donor. So the masses are the same, but of course the rest has to be totally different. It has to have a different separation in a different orbital period. And okay, so I get results like this. This shows the accretion rate, where the yellow would be just the wind rate from the AGB, and the blue is the accretion rate calculated from the Van de Hoy-Littleton prescription. So we can see that the accretion rate is highly correlated with the wind rate. And this red line here is the wind rate from the Roche lobe overflow model. And it's basically the same throughout the whole time of the whole run time, which is about a few hundred nova eruptions. I'm going to skip that because I don't have much time. Here we can see the blue would be the wind and the red would be the Roche lobe overflow models. And so obviously so this is the AGB star. So obviously the AGB star is rapidly losing mass. Sorry, this is, yes. So this is the AGB star, which is rapidly losing mass. And what's interesting, and so this was, and the thick red line is the main sequence star, which loses mass much slower, but it's these thin lines which are more interesting. They are showing the mass of the white dwarf. So the thin blue line is the white dwarf in the wind evolution, which actually gains mass. And that is while in the Roche lobe overflow, it's losing mass. And that has to do with the rate of accretion. As a side note, I will mention that when the accretion rate is higher, it allows the white dwarf to retain mass after an eruption. So what this is actually showing is that a white dwarf may be able to grow due to nova eruptions with an AGB donor. And provided the time there's enough time, it may actually be able to reach Chandrasekhar mass, which means that it might be a progenitor for a type 1a supernova. Another thing that we see here is if we compare the recurrence period, so I'll just put this there. This is just a scrunched figure of the one that I showed before, showing the accretion rate. And I just want to show that when the accretion rate, if we look at the blue curve here and the blue curve here, when the accretion rate is high, so obviously the recurrence period is low because it reaches the critical mass faster. But what we see is that the wind evolution can go through many scales of recurrence period, can be a few thousand years between eruptions, and it can also be just a couple tens of years, which means that it can actually show recurrent nova. And so there are times, so wait a minute, so wait, I was warned that I only have 2 minutes left, so I want to continue.
No, even less now.
Even less,
so
yeah,
you know.
I'm really
You're running
done.
overtime. So.
I'm really almost done, okay? Just 1 more minute. So what we have here is two parts in this evolution run, where the top part is from, we can see from this circle here, where the two runs had identical accretion rates. And then we can see that also the amplitude of the eruption is very similar. But if we look at the bottom one, that would be in this area here, where the accretion rate in the wind is much, much higher. And then the amplitude of the eruption is much lower. And it's much lower, and the recurrence period is much higher, and it looks very much like other recurrent nova from Roche lobe overflows. And I think this is my last slide, and I can even skip the last slide. And I will just sum that what this modeling was showing is that assuming the mass that is accreted onto the donor, onto the white dwarf, is solar composition, then the only thing that matters, the only thing that will affect the way that what eruption will occur, what will be the amplitude, what will be the abundances, which I skipped, and what will be, if it will be a classical nova or anything else, is determined only by the rate of accretion. So if we can get the rate of accretion that we're looking for, so that's what will determine if there can be a classical nova or not. And what I found for this specific model is that if we take an AGB and we put at the right separation, we could get the required accretion rates to produce the classical nova. And there are a couple observations that of classical nova. That's it.
All right. Thanks for your talk. Unfortunately, there's no more time left for any questions.
Wow.
Because 5 minutes over time. But in any case, if somebody has questions, please go and ask them on Slack. So go and head over there. So if you could please stop sharing your screen.
Oh, yeah.
And then, thanks. And then Andrea Chiavassa can start sharing his one. So he's from the Observatory of Nice. And Andrea will talk about the atmospheric dynamics of AGB stars unveiled by Gaia and interferometric data. Thanks for sharing your screen, and go ahead and start the presentation.
Can I go? Okay, thank you. Thank you, everybody. So good morning, good afternoon, good evening, depends when you're looking at this presentation. So thanks for letting me give a short talk about how we can unveil the atmospheric dynamics of HB stars. Yeah, I'm actually just pointing out also the still collaboration on this work is with Ben Fright. He should be here as well, man. Katerina Kravchenko, Matthias Schultheis in Nice, that should be following also now the talk. So yeah, I will start not going too in detail because this has already been said several times about AGB star, but I want to show anyway this image, which is a synthetic image that I will show it later in Gaia filter, and the comparable size of the sun that you can see with the small dot. And I want to really briefly remind what is really important for the context of HB stars in the context of more large stars is among the different parameters, stellar parameters we can detect is the mass loss that is extremely high when compared to the sun that you can see on the left, top left, bottom left, sorry. And this ejection of material that we really need to understand in very, very details. That's why I will show the models that we use for interpreting this part. Really have an impact on the evolution of and the region of elements of our galaxy, the dust production, stellar evolution of these stars in general. So it's very, very crucial to study this engine of our star engines that actually enrich with chemical elements and are actually the building blocks of the planets and life to come. But if we go now to the context of Gaia, if we have a look at what is done until DR2, but the DR3 is very similar, you see here the motion in Gaia absolute magnitude. We have the absolute G band magnitude, so we are indivisible now, with respect to the blue and the red color. And you see that the long period variable, this part here, is constellated by very, very lot of stars. This star actually a long period variable in terms of magnitude, luminosity amplitudes and variability timescales. And these timescales are very well covered by Gaia itself. And most of these LPV variables are cool luminous giant stars or red supergiant stars as well. So we really need to study those. But I just want to show what happened actually on the surface of the stars that actually affected the stellar parameter of the stars. So if you have a look to the sun, we have what we call the granulation. So on the right, we have an image of this taken with the Swedish telescope. And if you have a look to the synthetic images of courtesy of Matt Carlson here, we see, so the granulation, so the surface dynamics is postulated by convective movement that pump up the energy from below, and this actually affected the size. The stellar parameter of the stars actually affected the size and the shape and the number of these granules. For the Sun, we are under so 10,000 of granules. For this evolved star, the situation is very different. But why? So it's principally due to the low surface temperature, but also to the very, very low surface gravity. So we have just an image here on the right. We have the Sun. Most of the convective part of the Sun is just a very, very upper layer, a very upper part that actually contributed to the emerging flux. So what we actually observe with telescope is coming from this very thin part. But for AGB stars, this comes from the envelope is much more diluted, the surface gravity is much more lower, and we have very larger convective cells that go very deep in the stellar photosphere. And if you have a look to the radius, we are more talking about 200 stellar radii for this AGB star, while the Sun, of course, is 1 solar radii. So the situation is very, very, very different. So what do we use to study this thing? So we use radiative aerodynamical simulation of stellar convection. So they solve the compressible hydrodynamics, conservation of mass, energy, and motions, coupled with not local radiative transfer and the tail opacity. We do this, of course, with cobalt, the only code that can actually do this. And you have an example of video on AGB and supergiant stars. And coupling this with a 3D radiative transfer that is a code I did fairly just more than 10 years now during my PhD thesis. Do we extract so interferometric, spectrometric, photometric, and astrometric observables? That is actually what we're gonna use now for Gaia. I also encourage you to see Katerina Kravchenko and Masko Witkowski talks on Friday. They will talk it again, either on the use of this simulation or on the simulation itself. So basically, we take the temperature, density, velocity structure from the simulation, and we compute at very, very detailed opacities at whatever wavelength from the visible to the far infrared, the emerging flux or images that we actually compare to the observables. But how do they look at this the simulation inside? So if we make a cut, horizontal cut in this sense here, we have here the temperature or the density structure. The stellar is in the up, stellar center is in the up, the outer layers on the bottom. So you see that the configuration is very heterogeneous, permeated by random shocks. But we really see even better now if you look to the velocity. This velocity structure is not homogeneous. There are shock variation and in the opacity run, and this velocity dominates, and we really see the shocks. So we really see the shock front in the red. Red is actually receding us, and the blue is approaching to the observer, which is below. We have convective flows that have Mach numbers very high, and all these temperature inhomogeneities and velocity inhomogeneities actually affect a lot the emergent intensity, and so all the observables we want to compare to. So I start with Gaia now, if it goes. So the photocenter variability. So you have here now the Gaia G-band images computed for one of the AGB simulation from Bernd Freitag 2017 paper. I cite this a bit later. If you have this white line, which is basically the barycentric position, if there were no inhomogeneity on the surface, and we can predict then the movement of the photocenter displacement of this due to the image in the Gaia range during the Gaia missions, and we see this it's very, very different from what we could expect from the crossing two red dashed lines. And the funny thing is that this is very, very linked to the surface gravity and effective temperature, but in particular to the surface gravity, because as soon as the surface gravity is lower, the star is larger, let's say it's more diluted, so the turbulence and the convective movement have a larger impact on the images we compute then. So you see then for log G minus 0.50 and so on. So you see that the increase, there's clouds increases, and it becomes very, very pathological, let's say, for very high, very low surface gravities. So this is a clear correlation that we will see in a couple of seconds in next slides. But we actually measure the average values of this photosynthetic displacement. And the idea is to use this as a proxy to detect the convection-related motion in Gaia observations, but not really on the parallax measurement, but actually on the parallax error of Gaia. So now we have a plot on the left. You have then on the y-axis, sorry, the Gaia observation parallax error for a series of observations. So DR2 here. So they are the black points with error bars. And you have the photocenter variability that I just showed you a second before for the red stars. So you see that basically the convection-related variability actually accounts for a substantial part of Gaia DR2 parallax error. And this is even more true with the Gaia early DR3 data from December last year. So these points are very getting close to the observation. And one particular point is this one here, where there is a HB style we can actually observe with interferometer, which is Seal Lake, for which we have, of course, the next simulation. So we did that. So this is the coupling with interferometric part. So we observed this star. We make an image. So you have on the right the square visibilities as a UV coverage done with Chara. So Chara has very large baselines. We can really see details on the surface. And we see again that there is a displacement. So we reconstruct on the left the interferometric image. We see a spot. We see that the barycentric position is not where it should be. And we interpret this with a 3D convection. So on the right, there is the synthetic image. Then on the center, you have the convolved one with the interferometric beam. We could actually explain and detecting and characterize this convection-related structure on the stellar surface of this particular HB star, which is part of the Gaia data. So we are actually including the loop. We indirectly see the impact in the error with the photocenter displacement, and now we see really the convection on the star. So we can really see that the convection is actually acting on Gaia and making these error bars. But then, okay, we get back to this plot here. From this, and taking just the red stars, we can actually making correlations with the important parameters and stellar parameters of the star. So in this case, the logarithm of the pulsation period. So the standard deviation of photocenter displacement actually correlated within the simulations, which is actually good with the pulsation, and also with the surface gravity. These two things, the pulsation actually gives an information about the stellar mean interior properties, and the surface gravity, as I said before, actually govern the size of the granulation part, and so the photocentric variability. So the two together, starting from Gaia, parallax incertitude, and interferometry, we can actually have a unique way to determine mass, radius, and convection properties of HB stars using, of course, 3D simulations here. So this is the plan that we are carrying out since a couple of years now. And what's next in the next few years? So the first thing is to study, again, with interferometry. So we are applying for gravity now to observe. So gravity is a 4 telescope new generation, ESO new generation instrument, not so new generation, but still going on. In which is observing K-band. The K-band is very nice because we have all these CO lines you see in the bottom here. When you are looking,
2 minutes.
Yeah, when you're seeing at the top, the continuing part, and the bottom part, you have different morphology of the stars. And so the study of differential phase in this case can actually give us an idea about the photocenter displacement. And I finish in the last 2 minutes, the work in progress we have now with Gaia data. So we want to study now the photocentric and the radial velocity predicted for HB stars. First point, you see the photometric BPRP filter are very important, of course, for Gaia to determine the stellar parameter of the stars. Again, this is very affected. You have an example here where you have the BP and the RP band, so the blue and the red part of the Gaia filter. You have a large variability during, so it's the gray clouds with respect to the average value of the flux. So this is actually affecting the error bus you determine on the stellar parameter of the star. So we aim at interpreting this using our simulation to have a better parameter on these stars, again, using the error or on the photometry. We are going, I mean, this is already part of our ERC and extended the grid of this global simulation, ERC ongoing by Susan Hoffner. And this, again, you have a parallax error bar as a function of luminosity. You see we have much more, a lot of Gaia stars observed, and the dot are the simulation. So we want to increase this to cover as much as we can. And of course, the last point when Gaia DR4 will be available, and finish on this, is the time dependence. We have studied the time resolved Gaia observables and to study actually the effect of convection on the stellar parameter, and give this final point to eventually combining our unique global view and systematically study the properties of convection in other stars than the sun using Gaia and interferometry. And I think I finish on this.
Thanks a lot, Andrea, for a very interesting talk. If there are any questions, please raise your hands in the chat, and then, well, you can ask your question. So far, I don't see any questions appearing. Either we're tired or we're hungry. No, Leen has a question. Please go ahead.
Thanks, Mary. Thanks, Andrea, for this very interesting talk. I was wondering, so you have shown that plot where you have shown the correlation between pulsation periods and the photocenter variability. This is for periods, if I have seen correctly, above 100, 150 days, something like that. So what about this very low pulsation periods, potentially around 60, 80, 100 days? What is then the deviation that you see?
This is not, I'm not sure. This is something that we should also ask to Ben, whether how long have we gone with the simulation. This simulation comes from the 2017 paper, which are actually covering this range of periods only, which is between 90 and
above. Yeah.
So I don't know how to answer for that, but I suspect it will be the same actually, because this is very,
but
you mean the same,
it would follow the same decreasing trends.
Yes, I would expect that, but of course this is this must be tested. But still, as you see, there are not so many points as we discussed before. We need, of course, these are models difficult to compute as well.
Yeah, absolutely, I can understand.
But I would expect the same.
Yeah. And if you look then to so you have now given the answer from the perspective of the models. What about from the perspective of the Gaia measurements?
Yeah, the very important point is this one, is really the study of the time-dependent observables. This will be really the point that models need to advance. We really need to see how much, so Gaia DR4 will be very crucial in this sense, because we can really follow up the photometric and photocentric variability as a function of time. Yeah. And this will be really crucial to compare to constrained simulation. So this, from the model side's point of view, this will be really the crucial part.
Okay, good, thanks.
Thanks, Leen. Michele, you have a question. Please go ahead and ask.
Yes, thank you. So this is Michele Trabucchi, and thanks a lot for this very interesting talk. So if I understand correctly, your plan is when Gaia DR4 will be out to use the full astrometric and photometric time series to constrain the motion of the photocentric motion. Is that right?
Yeah, the idea is to use to extract. The idea is to extract the stellar parameters of this star, which are very, very difficult in general with different techniques, and we think that we can get as much closer to the solution using this way, indeed, coupling On one side, Gaia, and the other side also interferometry. I also have to add one thing that I didn't say. Of course, there is a one important point also with Gaia itself, that it depends on the cover time of observation, that also you see on the bottom is increasing. So the error bar will actually decrease as much as we have more points from Gaia, but until it will be intrinsical, I mean, the final solution will be intrinsical error, have an error bar due to the movement on the surface of the star.
Okay, I understand.
This will change as well.
With a general curiosity question, could you comment on what you think could be sources of error, so to speak, that add upon the photo center motion in this Gaia data? What are kind of noise could there be that could be due to pulsation, convection, to circumstellar environment?
Yeah, one point could be also, of course, multiplicity of the stars. This is, of course, one thing, yeah, that I didn't mention, but is basically very crucial for this kind of stars as well, as has been said before. Most of them may be binaries. And then also Gaia intrinsic error, I see that maybe we were concentrating on the physical, let's say, try to mimic the physical part in the error bars. But of course, we have also systematics in Gaia data that will be also solved in the next release, which is also will probably also decrease a little bit the error bars of Gaia.
Okay, thank you very much. It's very interesting work.
Thanks to you.
Alain, we have time for a very quick question. Just a quick question.
Yes, Andrea, hello. So I believe from your last figure that this sends us a signal to be cautious when using the Gaia parallaxes for HB stars, right? So because there might be large errors involved.
You mean this plot, Alain?
Yeah. Yes. Yes.
Yeah. Yeah, this parallax error comes really from Gaia early DR3. So on the y-axis, on the x-axis is a error bar we estimated from the luminosity from different catalogs. This is what you asked, or but probably is underestimated. Maybe, yeah, I don't know. So this is the point. We have not, I mean, we still have to wait for, I mean, we have some results, but of course we have to wait a little bit to more development in Gaia. And we definitely need to go from the simulation, from the dot we see this to lower luminosities and shorter period stars as well, where most of the Gaia data are. So there is work to do.
If anybody else has other questions, please ask them on Slack. So there's a dedicated day one channel. And Andrea, thank you for your presentation. And thank you to all the speakers of this session. I would like to again point out that everybody should register for the diversity session, or just say yes or no, basically. I again pasted the link in the chat for your registration. So now we have a half an hour, well, a bit less than half an hour of a break. And at 1/4 the next hour, so for me here in Belgium, it's 1:15, the Speed Meet a Mentor session will start. So mentors and mentees, please make sure that you're on time, because it is a time-sensitive speed dating sort of thing. Thank you everyone for tuning into this first session of Delve, and hopefully see you tomorrow or the day after tomorrow, whenever you're awake. Thank you and goodbye.